All right. Hi, everybody. Today we're hitting topic 28. This is the last topic for the week. And tomorrow's study group, I'll be introducing the project, but more and more project details will come over the course of next week as well. Because project intros come in tomorrow, please indicate whether you want to work on this project by yourself or with someone else by the end of today. Then tomorrow I'm going to create the pairs so that we can start you can start collaborating on the project if you want to. Technically, if you're working by yourself and you've already indicated, you can start now, but yeah. Okay, what else? Don't forget your blogs. Again, I'm gonna keep saying blogs until I get most of the blogs in. So don't forget to get your blogs done. Again, sooner the better. And yeah, also reminder that I gave you all that little Python programming function task. Now that if that function works, you should be also able to implement your function with this model too. So if you want to test whether your function can generalize to all sorts of different models, which with every model that we're learning, it should be able to work as well, because all of these models, as long as they come from the scikit-learn library, which this one does, it should work with your function. All right, let me see, is there anything else I need to mention? Yeah, I think the most important thing, indicate if you want to work solo for this upcoming project. And then tomorrow I'll talk about some data set details if you want to source your own data. Okay, so today's algorithm, we're going to talk about Bayesian classification, which is also a non-parametric model, because yesterday I talked about, parametric versus non-parametric model. There are no assumptions. You'll see here that there's an independence assumption, but that's not about the model. And another thing to mention is this is a purely probabilistic model. I know I mentioned that machine learning is a big part of this phase, but that's not this model. This model is purely calculating probabilities and classifying your data points based on probability. Now, for more context, naive Bayes, which is the model that we're going to be talking about, is actually best used, or not best used, but instances where you see naive Bayes being used the most is actually for text data. So in natural language processing, which is something that we're going to talk about in much more detail next phase. But as a little sneak preview, we're going to be dealing with text data today, just so you have an idea of how we treat text data. Even though we're talking about text data today, this model will, of course, work with your numerical, whatever data set any numerical non-text data, it will also work. All right, so to introduce the classifier, naive Bayes classifiers are linear classifiers that are known for being simple and very efficient. The probabilistic model of naive Bayes classifiers is based on Bayes' theorem, and we'll get back into Bayes' theorem later. And the adjective naive comes from the assumption that the features in the data set are mutually independent. So that means every feature has to be mutually independent and one isn't affecting another. So an example of features that are not mutually independent in your last project with the housing data, things like square footage and number of floors and number of bedrooms, bathrooms, those are all not mutually independent because they're definitely related to each other. The adjective naive comes from the assumption that for this model to make sense in a probability world, features should be independent. However, in real life, that is never the case and is naive because even though our features are not independent, we still use this model and it still tends to perform pretty well. So yeah, even though this independence assumption is often violated, so you actually don't have to worry about checking to see whether your features are related or not. You don't have to do that. So yeah, naive Bayes classifiers still tend to perform very well under this unrealistic assumption. Especially for small sample sizes, naive Bayes classifiers can outperform the more powerful alternatives. So to set up the problem that we're going to work through, because we're going to work through the probability math of how this algorithm works, we're just going to classify statements on whether they are related to sports or related to politics. So here we have 3 sports statements. The match was close, coaches agreed on a strategy, played in a sold out stadium. And then we have a couple politics statements. So world leaders met last week. The election was close and the officials agreed on a compromise. Now we have this test statement that is kind of ambiguous. You could say it's both, but we're going to see which label our classifier will decide to classify this statement as. And this test statement is world leaders agreed to fund the stadium. You might have your ideas of which label this statement should have, but let's see probabilistically which one it is. So yeah, seems like it could be either sports or politics, probably both, but we'll see. Okay, let's revisit Bayes' theorem. So Bayes' theorem is all about conditional probability, where you take into account some sort of prior. So this is the most common form of Bayes' theorem. You have probability of A given B is equal to the flipped probability, flipped conditional probability multiplied by probability A divided by probability B. If you want to get into the proper terms for each of the parts of this Bayes' theorem equation, this result is the posterior probability, the probability at the end after considering, your given statement. This other conditional is the likelihood, this is the prior probability, and this is the predictor prior probability, which will make sense in a little bit with more context. If you want to expand on this, this is also partially the, I believe, this is the chain rule probability, I think. Okay, so let's go back to our context of those 2 classes and 6 statements. If we want to apply this statement to the context of classification, this is the general equation. The probability of L, and L is just like a label, given its features, is equal to this. And this is just plugging in L and features into our Bayes' theorem equation. So if we're trying to decide between 2 labels, let's call them L1 and L2, then one way to make this decision is to compute the ratio of the posterior probabilities for each label. So if this is the equation for figuring out what the probability of having a label is, given its features, like what is the probability of it being class 1, class 2, it can also expand to multiple classes. Given its feature data, its X data, we can apply this equation. And we can also compute the ratio of these posterior probabilities. So let's say we have a 2-class problem, which is what we have. We can take this ratio here. It's basically L1 divided by L2. So therefore, this denominator kind of cancels out. So the probability of your features, which in this context also doesn't really make sense, that's unnecessary for the calculation of naive Bayes probabilities. So yeah, if this is our ratio and this is the probability of it being, let's say, politics, and this is the probability of it being sports, if your ratio is greater than 1, it is likely to be a politics document. If your ratio is less than 1, it is likely to be sports. So in the context of our problem, these are our equations. This, let me annotate it real quick. These are our 2 naive Bayes equations, and this one down here is just 2 of the naive Bayes equations put together. All right, we're going to break this equation down in the next section, but any questions at this point? Awesome. Okay, so how do we calculate the probability of the class? So in the general form, how do we calculate this PL, probability of a label? And in this case, how do we calculate the probability of politics and the probability of sports? So this is essentially the distribution of the probability of either type of article. So we have 3 of each type of article in our current set of example documents. So there's 3 sports and 3 politics. If we were to just throw all 6 of these statements together, what's the probability of it being each? It's 1/2. So it's just number of documents, number of sports documents divided by total number of documents, number of politics documents divided by total number of documents. So yeah, here we can see that these are our politics documents. So the probability of politics is going to be 0.5. probability of sports is also 0.5. So here you can see I'm taking the length of politics divided by the sum, length of sports divided by the sum. Okay, so that's the easy part. Let's move on to some of the conditionals. So how do we calculate the probability of document given that it is politics? And so when we're breaking down the document, we first have to break the phrases down into individual words. So this is kind of a sneak preview into how we do NLP. One method of treating text data is by treating each unique word as a feature. So if you had like a bunch of text data and in your entire data set you have 500 unique words, you're going to have 500 columns in your X or 500 features. That is one way that you can treat text data, and it's actually the first way that we'll talk about when we get to NLP next phase. So yeah, we're going to break the phrases down into individual words with the hope that these words actually tell us more, since we likely have never seen this exact document before. So this is our test statement. Okay, now how do we express the probability of a phrase given that it belongs to politics label? It is just the, and this giant pi symbol just means product. So it is the product of the probability of each word given that it is politics. And the probability of each word given that is politics is calculated by the number of that word occurring in all politics documents divided by the number of total words in politics documents. So it's sort of like a word frequency within the class expressed as a ratio. So what if you see a word in your test statement that your model hasn't encountered before? The numerator then becomes 0 and the numerator becomes 0. So therefore we have to have Laplace smoothing. If you want to correct for this 0 value, you can add a alpha term. And this alpha term will just stop your numbers from going to 0. We'll see why we don't want our numbers to go to 0 in a bit. So you can do this Laplace smoothing by adding alpha here, and in your numerator, you'll also add alpha multiplied by d, where d is the number of features. Now this, you don't have to compute, and actually any of this you don't have to compute. This Laplace smoothing, this alpha term is one of the hyperparameters that you can tune in your model. So let me actually pull that up real quick. Let's see, scikit-learn. There's a couple different naive Bayes models, and I'll go more into that in a bit, but here, you can see smoothing. So variance smoothing is basically our alpha, what we can use to basically also prevent overfitting. That's something that alpha does too. All right, so how do we calculate the probability of document? We don't have to, because again, they kind of cancel out. So putting it together, we can apply our equations and we can figure out our word frequencies, and we can calculate the probability of our test document being in either class. So as you can see here, the most granular thing that we're computing are these word frequencies. So let's start with that. So this is all of the unique words that appear in our data set. And we're coming up with like a word count table. Oops, sorry, I'm just trying to fit everything perfectly there. Okay, cool. So as you can see, it's sorted based on the frequency in sports, but there are words that don't appear in some classes. So for example, the word the appears twice in each. The word match appears once in sports, none in politics. An example of, yeah, all of these words at the bottom, world leaders met last week, election officials, appears once in politics, none in sports. Now with this table over here, we can take a look at our test statement. World leaders agreed to fund the stadium. So we're using 1 as our Laplace smoothing, value. So that's what this +1 is. Let me zoom in a little bit more. That's what this +1 is. And this +30 is alpha times d. So that's this part over here, because there's 30 unique words. So therefore we have alpha plus d. So therefore all of this computation is being done. So for the word world in politics, It appeared once in our politics documents, and then therefore we add 1, 15 plus 30, we get 2 out of 45. And we can compute all of these probabilities for each of these words, for politics and for sports. Again, we don't have to do it, the algorithm will do it for us. So with this, and if we were to save all of our data, and this is through some function. So through this, I'm going to make a vocab. I'm also going to count the length of our full vocabulary, our sports vocab, and our politics vocab. And here there's a function that finds the number of words in each category. And therefore we get our word counts. So you can see here our sports word count and our politics word count. Putting all of those together, literally just applying all of these formulas, we can end up with the likelihood of this test document belonging to each class. So pretty straightforward. It's just an application of Bayes' theorem. So what we're doing is we're comparing these two likelihoods. Now the two likelihoods, if we go back up to our equation, the two likelihoods are this number as well as this number. And all we have to do is compute or compare which one is more likely, and that will be the classification. So if we go down here, from here you can see that the numbers are very, very small, but we just have to compare which one is greater, and that's what it'll be. So in this case, the likelihood of politics is greater than the likelihood of sports. So therefore, this example text will be classified as a politics article. Questions about that?
Can you weigh the words differently?
Good question. So I think by default, no. I don't think you can weigh the words differently. However, and we will get to this in natural language processing next phase, you can do a lot of word cleaning. For example,
You can just use the words that you don't care about.
Yeah, exactly. For example, words like the, probably you don't want to use. Like these are called stop words, like in, a, on, all of these words. We'll go through more text processing processes next phase. But yeah, that's how you, I guess, could weight words. And this is also only just one of many different methods that we use to deal with text data. So this is the simplest one to start. But yeah. All right. So based on this, some things to note. If you have a word in your data set that is evenly spread out throughout your labeled text, it's likely not going to be very useful. So for example, the word the, it appears both in politics and sports 2 times each. Because it appears the same number of times across both labels or both classes, your model isn't able to see what the word the has, or how do I rephrase this? Sorry, my brain's a little jumbled today. Basically, the word the, your model's not going to see, if you see the word the, is it more likely going to be politics or sports because it appears evenly throughout the both of the classes. Does that make sense? My English is not working today. But that's something to note. In your calculation of probabilities, it will not really add to the likelihood if your numbers are similar. So here you can see that for word like 2, this number 1 out of 45 is the same, which is therefore when you multiply it all together, it's going to have the same effect across both classes. Whereas a word like world, which appeared more in politics, actually world leaders agreed, these words appeared more in politics, therefore you have a higher fraction. It's going to help lean your model's decision more towards politics. Yeah, so therefore you can sort of see here, because we have world leaders agreed, which were all words that were, much more politics versus sports, or I guess just world and leaders. those words help to push the model's decision towards politics more than sports. Because I think for sports, the only word that helped push it more to sports would be stadium, if you were to compare the two fractions on either column. Oh, sorry about that. My language is a little scrambled today. Okay. So in summary, and we're going to get to implementation in a bit, so don't worry. So in summary, naive Bayes is extremely efficient. It's actually one of the fastest performing models because it's really just computing like counts of things and doing probability computations. Also, when the assumption of independence holds, a naive Bayes classifier requires a lot less training data and can perform better than models like logistic regression. Also can perform better with categorical inputs. For numerical inputs, one has to assume a normal distribution, but again, that assumption is not usually important to the model's performance. But yeah, with logistic regression, and you sort of saw that with linear regression as well, when you have a lot of categorical variables, it is tough to get your metrics high. But with naive Bayes, it doesn't matter. Okay, so some cons. Naive Bayes is known as a bad estimator. So probability outputs from predict_prob are not to be taken too seriously. Now that is kind of different from saying that it's not good as a classifier. It is a poor estimator, but it's an okay classifier. What I mean by bad estimator is here you can see that our likelihoods were very, very small. It takes a very conservative approach to figuring out, what's the probability that something is going to belong to one class or the other. That's what it means by bad estimator. I'll show you all what predict_prob is in a little bit, but basically what you can do is from your test data, you can actually extract the likelihoods for each class. Also, we're assuming independent predictors, but in real life, it's almost impossible that we get a set of predictors that are completely independent, which is again why it's naive, but amazingly still works a lot of the time. Okay, so I'm going to run through the scikit-learn implementation of naive Bayes, and we're going to use a bunch of text data. So what we're doing is we're going to get news data through the scikit-learn data sets. Okay, so this is what our data looks like to start. We have, let me bring up our DF stream. This is what our training data looks like. So here we have our targets of 0 and 1. In this case, I think 0 is going to be sports. Oh, they're all, yeah. 0 is going to be sports, baseball, and then 1 is going to be politics, I guess miscellaneous. And here we have our train and our test data. Our train data right now just looks like this, which we'll clean up in a little bit. Cool. So these are our target classes: baseball, miscellaneous, politics. If we take a look at our info, that's kind of the same. And if we take a look at our train and test value counts, fairly even. We do have a few more. The proportion of sports articles is a little bit higher, but that shouldn't be a big issue. And this is what a text looks like. Don't worry about cleaning this up yet. We will definitely get to cleaning this in the next phase when we talk about natural language processing. Okay, so really, really briefly, the process of turning text from this into something that's numerical is the process known as vectorizing. So vectorizing text, whenever you hear that term, is just the process of taking, your words and turning them into some representation by numbers. And as I mentioned, one of the simplest ways to do that is just by taking a word count where every column will be a unique word. So scikit-learn does have this built in. So I'm going to run these, but I'm not going to talk about what exactly this is doing. But what this whole chunk of code does is it creates a data frame that has a column per every unique word. And then all of these values will be the associated word counts. So a lot of zeros, as you would expect. In this case, you have like 19,000 columns, which is ridiculous. But yeah, this is without any like word filtering. So not to worry about that for now.
What are the rows?
Each row is an article.
Gotcha, thank you.
So the numbers will correspond to let me see where it comes from. I think, yeah, the numbers will correspond to these. So the index numbers will still correspond to each other.
Thank you.
Cool. So basically, like article number 1, I guess, has 0 instances of all of these. But you can rest assured that there is some data in there. So if we look at extreme vectorize, just out of curiosity, we'll do a sum. So there's like 227 instances of, I guess, 0, 0, 2 instances of like N Austin. So these words exist. It's just a lot of zeros right now. But this is technically still data that we can throw into our model, which is what we're going to do. So we're going to do our chain test split. We have our chain test split over here. We're going to instantiate our naive Bayes model. So there's a couple different kinds of naive Bayes models. Now, Gaussian naive Bayes is one of them. Other ones, which I don't know if they list them here, but I do list them in the summary, the model summary sheet. And I think I also mentioned like really quickly when to use which one. You could also perhaps test all of them to figure out which one works best on your data. But yeah, we're just going to use the default naive Bayes. For naive Bayes, the only thing that you have to tune is this smoothing parameter, which is kind of like regularization as well. If you want to give it prior probabilities, you can as well, but it can infer from your data. And by prior, I mean like the proportion of rows in each class. So let's just go with our default to start, and let's fit our model and then get our predictions on our test set. Our training confusion matrix looks like this. You can see that we got a perfect classification, and we can figure out our accuracy, precision, recall, and F1. This is all for our training set as well. Perfect as well. And for our test set, our metrics are a little bit lower, which is to be expected. Maybe it's a little bit overfit, but this is what our results look like. As you can see, a lot of this code, a lot of these functions, again, exactly the same as how you would implement any of the models that we've already talked about, which include logistic regression. Yesterday, what did we talk about? I forget what we talked about yesterday. We talked about K-nearest neighbors, right? So implementation, exactly the same. Cool. Any questions? Awesome. Though this example is a text example, it works exactly the same way with your numerical data as well. Cool. Now I want to talk about the predict proba from earlier, which is something that some models have. If you want to see what information you can extract from your model, I do recommend taking a look at here, the methods. So predict proba is one of the methods that is built into the naive Bayes model, which basically shows you the probability estimates for your test set or even your train set. So what you can do is, what did I call my model here? Model. Okay. So if I do model dot predict proba, and we're gonna do X train. Yeah, let's use X train. What it returns us is an array of probabilities. Let me just throw this into a data frame. Data frame this, and then columns equal to, let's just do sports and politics. This is the associated probability for each data point. Now we take a look at X test, it gives us that as well. This is probably rounding off too. But yeah, this is information that you can extract. I will say that if you have more classes, this will probably be more interesting because you can see that, all right, maybe it predicted class 2, but the probabilities for class like 0 and 1 were maybe like just a little bit lower. So it can be something that you explore as well. So out of this, you get predict proba. You can also get predict log proba, which is basically the logged version of this. Predict log proba, which are more numbers that look like this, so on and so forth. So within your other models, especially the ones that we talked about before, for example, we talked about K-nearest neighbors. This is something I didn't talk about yesterday, but you could technically, KNN classifier, where is that? So within K-nearest classifier, you can also get your probability of prediction. So this is something that's good to check out for any model. I would say more relevant for whatever you pick your final model to be as you're doing your interpretation and analysis. But good to know that, you know, these are one of the methods that you can employ in your analysis. All right. Well, this model was a lot of repetition from, you know, last phase's work on probability. So there's not much else to talk about, but does anyone have any questions regarding this model or pretty much anything so far?
So
There are,
go ahead, sorry.
thanks. So I know that there's a Gaussian naive Bayes, but there's also like a Bernoulli and a couple other ones. Can you talk a little bit about the applications?
Yes. So I have it in our homeroom, I think. Let me check real quick. Down here, classification model summary, I did make a table that has each type. Oh, I guess I don't really talk about one. Each one has, so I don't know it off the top of my head, but I know that if you have more than 2 classes, you typically want to use multinomial naive Bayes. And the main difference between Bernoulli and Gaussian, I think, is in the way that it does smoothing, because the overall equations, I think, are the same. Let's find out. Ooh, can we open this in Google Docs? Let's see. So that one is Gaussian naive Bayes, and then we'll look at Bernoulli Bayes. So this one is more suitable for, I guess, discrete data. Bernoulli one is more designed for binary or Boolean features. And I think it's just slightly different in the way that it does the smoothing calculation.
Okay, thank you.
You're welcome. Dimitri, you had a question too?
I think I forgot my question. It's okay.
That's okay. Any other questions? This isn't output nicely. Cool. Again, as your question.
Can you talk a little bit? I know you're going to go into more detail tomorrow, but if we wanted to find our own data set, like what we should look for?
Sure. Okay, so if you're finding your own data set, the dimensions of your data should be at least 1,000 rows, at least 10 columns. So same as last time. Basically, what you're looking out for is your target column should be categorical, versus last time your target column could be anything continuous. This time your target variable has to be something that's categorical. Now, I don't like, it doesn't matter how many different categories there are, at least 2, of course. And I would say try and get, actually, instead of 1,000 rows total, I would say, to be safer, at least 1,000 occurrences per category on average. So there might be some imbalances between the categories, but on average, try to get 1,000 rows per category, which I think you can see on Kaggle. So yeah, let's do a quick Kaggle search to see what we have. So we do, classification, perfect. So here we have, okay, stroke prediction data set as an example. Looks like you're using information about the person or about the subject. And then you have your target column, which is stroke. And you can see that 4,000 people didn't have a stroke, and then 250 did. This is an imbalance problem, but on average, there's still roughly, on average, more than 1,000 per class. We'll talk about imbalance during one of the office hours. But yeah, something like this would work. Other things to note when you're looking for your data, sometimes it's not immediately clear what your target column should be. And like sometimes, based on what the data is, you could choose between a few columns to be your target. One thing just to be aware of, or to keep in mind, make sure that the direction of causality makes sense. Your features should predict your target. So for example, if I instead wanted to predict, I don't know, predict age, I wouldn't use whether someone has a stroke to predict age. Actually, maybe you could, I don't know. But if you understand what I mean, just the direction of causality, make sure it makes sense. Cool. So yeah, I'll talk more about the data tomorrow. And I also have like another project guidelines doc that has a lot more info. So yeah. Any other questions?
Is there like a limit to the amount of categories, or is it just that we should use for the, so like if you used age, for example, and we broke it down to literally each age, or should we try to kind of consolidate to like, let's say 10,
Gotcha.
10 12
Yeah,
and lower?
that's a good question. If you have a feature that is continuous that you want to bin and make categorical, you can do that. Now, limit to the number of categories. I want to say keep it below 10. There's technically no limit, but once you get more categories, if your number of categories blows up, it's going to be very hard to pin down and adjust your models. So try not to have more than 10 categories. Also, like imagine your confusion matrix. If you had 10 categories, your confusion matrix will be like a 10 by 10 grid that'll get harder and harder to read.
Right. Oh.
But yeah.
Also, I remembered my question. I just didn't catch while you were scrolling. So we didn't do any transformations on this data, right? For the
Yeah.
model at all. Okay.
Yeah, so for naive Bayes is that this is one of the models that you do not have to do any transformations for scaling.
And if some scaling was done, would that ruin the model?
Ooh, that's a good question. I think it won't, because the probabilities are being computed within each feature itself. So proportionally, if you're doing a scalar, shouldn't affect it. If you're doing log transform, I can see that it might affect the probability a little bit. But I would say for the most part, no. But also there is no good reason to log transform something for this model.
But a standard scalar would be fine.
Yeah, that would be fine. I don't think it'll affect your results by much, if any, if at all. I have to think about the math a little bit, but I don't think so.
Yeah, no, I'm just thinking about the function that we're writing.
The function,
where
yeah.
things go. Okay, thank you.
Yeah, you're welcome. Okay, any other questions? All right,
Oh,
so
last question. Is there an equivalent? Can you do that second, not the confusion matrix? That's the word is the second thing that we did for the models yesterday.
Oh, classification report?
Yes, the report. That's right.
Yeah.
That's available for this as well.
Yeah, classification report actually just takes in classification report. It takes in just your like actual values and predictions. So you actually don't, it doesn't matter what the model is. You just need to get like the predictions and the actual, and you can produce the classification report.
Great, thank you.
You're welcome. Cool. I want to briefly talk about what I'm going to talk about tomorrow. I'm going to introduce the project, but there's going to be a few things that I won't be able to talk about, which I will continue talking about throughout the next week as we get to those things. Tomorrow, I'll also be talking about pipelines. Now, pipelines is our very last topic of the phase, but I think it is important to, or good to know now. So I'm going to talk about pipelines. I'm going to move that section to tomorrow, just because I think it's going to be useful for you all. Pipelines is basically what will allow you to combine your scalar with your model as like a model object, which is really, really cool. And I'll demonstrate that tomorrow. So yeah, that's what's coming up. Other than that, don't forget to do your blogs.
I recommend the pipeline stuff tonight if we have time. Would that be helpful?
Yeah, actually, yeah, I do think that if you want to like skip to the very end, I think it's topic 32. It's not, I don't think there are too many lessons in there. Let me actually go and find out. Phase 3. Let's go to student view. I believe there's not too much there. Yeah, it's literally like intro. There's like one lab there. So yeah, it's actually just like a implementation with scikit-learn, but I'm going to talk about, I'll just talk through how to use them tomorrow as well.
Okay.
Yeah, it's actually really neat. It like combines your scalar, it combines your scalar and your model together. And so when you do a dot fit, it will do the transformation process before feeding it into your model automatically. So it's super cool. And that's all. I'll briefly talk through that tomorrow. Awesome. Any other questions? All right. Well, if there's nothing else, I look forward to talking about the project tomorrow. Next week, we get into like my favorite models. So I'm excited for that. But if there's nothing else, Slack me all if you all have any questions. Do your blogs, indicate whether you want to work on this project solo on my message from 2 days ago. And yeah. All right. If there's nothing else, you all have a good rest of your day, and I'll see you all back here tomorrow. Bye, everybody.